Hello, mathematicians. My name is Matt DiSorbo, doing the algebra lessons for Skew the Script. Today's lesson 3.2 covers systems of linear equations, specifically the benefits of electric vehicles versus standard gas-powered cars. Without further ado, let's skew it. Welcome into lesson 3.2 of Skew the Script. Today we'll be talking about systems of linear equations. Specifically, you've seen them out on the road, Tesla electric cars. Elon Musk, the founder, gives the thumbs up, but maybe not when it comes to the price tag. These cars cost a pretty penny and can run you north of $37,000 a pop. However, the benefit is that they're good for the environment, right? Well, there's a little bit of a complication with that. Some electric grids are actually powered by coal, and the batteries used by these cars are often generated in cobalt mines. So our key analysis today will be if electric cars can beat the cost and even what they're touted for, the environmental impact of traditional gas cars. If you'd like to follow along with our lesson, check out the guided notes at the link below. Print or download the notes to fill out as you work through the lesson with us. Quick note, another version of this lesson is available in the New York Times. You can read about it, click the link below to get another version from your favorite news source. We'll be going through topics today. The first is constructing a system of equations. And the main question we'll obviously be discussing is, should we be buying electric? We've seen that Teslas are expensive, but they may pay off over time because they actually don't require gas. Of course, they run on electricity, they're less maintenance, etc. So what we want to see is at what point is buying a Tesla actually worth it? A good place to start naturally is the upfront costs. For an electric Tesla Model 3, it'll cost just about $38,000, whereas a Toyota Camry XLE, a gas-powered car, will cost about $8,000 less, about $30,000. So the upfront cost is definitely higher for the electric vehicle. You're going to save over $8,000 if you go gas. But what about the total cost? Because when you buy a car, you're not just paying up front, you're also paying for the fuel, which is gas if you have a gas car, and electricity if you have an electric car. You're also paying for maintenance. So let's think about each car's lifetime being 12 years, and let's say for simplicity that you own the car for all 12 years of its life. What will end up being the cheaper car overall for the entire lifetime? So we can take a look at the data, which is from an MIT lab, which compiled a data set of car costs and car emissions, both during the production of the car, which we'll get to soon, and the actual driving of the car. It assumes a bunch of typical variables, US gas and price, utility prices, driving distance, maintenance, etc. It also tracks the cost at every step. So the upfront payment of the car, the maintenance cost, the gas, the electricity, and the emissions at all these steps as well. In other words, it's a great data set to estimate some of the questions we're going to be trying to answer. So again, we start from the top with our electric and gas cars, about $8,000 more for electric. Again, in this stage, we definitely prefer the gas car because of cost. However, if we look at the per year cost, so gas, electricity, and maintenance, the Tesla is about $1,000, where the Toyota Camry is about $2,000. We very much prefer the Tesla when it comes to the per year cost. So to try to answer our questions of which car we want to own over what time span, we can actually create a linear equation where we allow Y to be the total cost and X to be the years owned for the car. So again, this total is the upfront cost plus the yearly cost times the number of years that we have the car. We're going to call that Y as the total. Say it equals the upfront cost, about $38,000, plus the yearly cost of about $1,000 times X, which is the number of years that we own the car for. If we rearrange, we're going to get Y equals mx plus b, every mathematician's favorite one-liner. And we can also fill out, we'll come back to the Tesla equation in a second. We can also fill out this equation for the gas car in a very similar way. Y equals the upfront cost plus the yearly cost times the number of years, rearranged to get Y equals mx plus b. So now we have our model for both the gas and Tesla. So again, we want to own the car for 12 years. What will be the cheaper option overall? Again, Y is the total cost, X is the number of years owned. So if we want to calculate how much 12 years will cost, we simply plug in 12 for X. In our first equation, we plug in 12 for X times 1,016 plus the upfront cost. You multiply 12 times 1,016, we get 12,192. Added together, we get a total cost of $50,182. Similarly, for the gas car, we plug in 12 months. We multiply by the monthly cost and the yearly cost, and we add it to the upfront cost. we get $54,326. So it looks like Tesla in this model wins. It wins by a good chunk, about $4,000. We paid just over $50,000 in the life of the Tesla, where we paid $54,000 over the life of the gas-powered car. So Tesla is cheaper, definitively cheaper over 12 years. Let's turn to our next topic, which is estimating kind of these questions with a table or graph, not necessarily the math that we were working through. And we're going to think of a slight twist on the question. We want to ask, we saw that the Tesla was worth it over 12 years. We want to say, how long do you need to own the Tesla for it to pay off? So maybe you don't want to own it for the entire 12 years. How long do you have to have it before it starts to be worth it? So we're going to start by creating a table showing the total cost in years from 0 years, so right when you own it, to 10 years. We have our two cars, the Tesla and the gas-powered Toyota. We have our two linear equations, and on the left, we have our table of years and the cost for each car. So to fill out each row, we're going to start with row 0. We just have to plug in 0 for X. So in this case, we have 2016 times 0 plus the upfront cost, and then for the gas-powered car, 2038 times 0 plus the upfront cost. Calculating these out, first term goes to 0, and we get the initial car prices when we plug in 0 for X, because that makes sense. It's sort of the upfront cost when we haven't owned it for any amount of time. Similarly, if we want to calculate the cost after 1 year, we plug in 1 for X, we multiply it out, we add these together, and you can see in the table on the left, we've entered these values for the cost after owning the car for 1 year. We don't have to do this calculation for every single row. We can know that for the Tesla, each year, the price will increase by $1,000, $1,016, because that's our slope, our X value. We can fill in those values super easily. And for the Toyota, the gas-powered Toyota, similarly, the cost each year will increase by $2,038, so we can fill in those values as well. And now we can look at those values and figure out at what point Tesla is worth it versus the Toyota. That's our major question. And we can see that in year 8, that's the first row where the Tesla value is lower than the Toyota value. It's cheaper to own. You can see that Tesla costs about $60-ish less than the Toyota total at that point, and that gap will only increase in later years. Now we can actually take this table and graph the cost of the car over time. So here we have x-axis is the year of the amount of time you've owned the car. The y-axis is the total cost. Tesla is the blue line and Camry is the gray line. We want to think about which graphical features show you the initial car cost and which car initially costs more. That's going to be the y-intercept when x equals 0, because it's the cost at y equals 0. You can see how Tesla, the blue line, has the higher cost. Then we want to think about which graphical feature shows you the yearly car cost and which car will cost more per year. In this case, it's the steepness of the line. It's the slope. It's the m in our y equals mx plus b equation. And Camry has more per year. It's a steeper line than the blue Tesla line. Finally, we want to look at which graphical feature shows you where the Camry begins to cost more than the Tesla. We can see that as we start increasing years of car ownership, the cost of the gray line is catching up to the blue line, catching up. Finally intersects, at the intersection, that's where the Camry becomes more expensive than the Tesla over time. This occurs just before the 8th year of ownership, so from then on, the Tesla will be cheaper. Finally, we can actually try to solve these with substitution or elimination, two excellent tricks in the algebra toolbox. We know that over time, electric cars can save you money. We've seen that after 8 years, the Tesla will be cheaper. However, we also noted in the start of this video that some electric grids are powered by coal, and some of the batteries are created in cobalt mines, which produce emissions. So are electric cars actually better and more green for the environment? And that's a question we can answer with algebra. Again, remember the data we had, it had all of our cost data, but it also had all of our emissions data at every step. So getting the materials, producing the car, driving, that sort of thing. When we think about the cost to produce the cars for the Tesla, we have this number. It's in kilograms CO2 per EQ, which just says the amount that making a Tesla produces in terms of emissions, equivalent to global warming potential of that metric. The higher a metric, the more emissions that it costs. And then the gas car, we can see that number is 7,400. So in this case, in terms of producing cars, The gas car is actually greener, which is very surprising. To actually produce a gas car, it's greener and less impact on the environment than the electric car. However, which produces fewer emissions over time? We also saw that the electric car was more expensive up front, but eventually cheaper over time. Is that the same case with emissions? So again, electric cars have coal-powered electric grids to actually deliver the electricity needed to run the car, whereas gas cars burn and refine gas to actually fuel the vehicle. So again, we saw the upfront cost, they're showed here, but then the yearly impact on emissions is far lower for the Tesla, about 1,300 compared to 4,500 for the gas car. So again, in a similar method to what we did with the costs, we can create linear models for each car's total emissions, Y, during the years of ownership, X. Very similar, except Y is emissions instead of cost. Again, the production emissions or the upfront cost are these numbers here, higher for the Tesla than for the Camry. And then we can add the yearly emissions. So that yearly amount times X, which is our years of ownership, to get our linear model. And then we can graph this sort of system of equations. We have two equations here, and very similar to the cost chart, we have these emissions over time. X-axis is years of ownership, Y-axis is emissions, blue line is Tesla, gray line is Camry. So again, we can ask the same sort of questions. When does the Tesla become more environmentally friendly? At that intersection point, which is sometime after the first year. But while eyeballing the graph is nice, it gets us an approximate answer. Let's try to figure out exactly when, to the day, the Tesla will become more environmentally friendly. And we can use algebra to do this. So we want to find this exact point of intersection instead of just eyeballing. To do that, we have to figure out where both equations Y and X are equal. So we can take our two equations and we can solve them via substitution. The way we do that, again, at the point of intersection, Y's and X's are equal. So we can substitute between these two equations, the Y and X values. So basically, in the Tesla equation, we know that Y is equal to that whole thing on the right side. So we can put that whole thing on the right side into the Y of the other equation, because all of this is equal at the intersection. Okay, so we plug that in, the 1368X plus 11074, plug it into the Y of the gas equation, and now we have this new substitute equation with a single unknown, a single variable X, which we can solve. So we just want to use our standard algebra toolbox here. We subtract 7402 from each side, that cancels out on the right, and now on the left, we have a kind of a smaller number there. So we have this new equation. We subtract out 1368X, which will cancel out the X on the left side and make the X term on the right side smaller. We have this new equation, and now our last step is to divide by 3157 by both sides. We get X equals 1.16. And that's our solution. So this is saying that the intersection point is not just a little bit over 1, it's exactly 1.16. We can see kind of our line there. And this is telling us that Tesla becomes more environmentally friendly after 1.16 years of driving, so about a year and 2 months, which is much quicker than it took for the Tesla to become cost effective. We could also wonder, what are the total emissions? What's the emission point when they actually cross? And that's basically asking what is Y. And to figure this out, it's much easier. We just have to plug our X value 1.16 into the equation. So we can plug it into our gas equation. We put 1.16 in for X, simplify, solve for Y. So we multiply those two terms out, and then we add these terms together. We get 12,651 for Y. Another way to solve the system, we solved it with substitution. We can solve it for elimination. And the idea here, again, important to remember that Y's and X's are equal in these equations. So we can just subtract the equations, and we subtract one equation from the other. And the nice thing is that the Y's will cancel out. They go to 0. So they have been eliminated, which is why this is called elimination. And we're left with an equation that just has one single remaining unknown, which is X. So we want to solve for X. We add 3157X to both sides to get everything nice and clean. And then again, this is probably looking familiar. We divide by 3157 to get X equals 1.16, which is the same as before. So fortunately, these two methods gave us the same answer. It would be concerning if they didn't. Finally, let's turn to the discussion portion of this section. We've certainly seen how in some situations buying a gas or hybrid car can surprisingly be more environmentally friendly than buying an electric car. Can you think of a situation when this is the case? And you can explain this by sketching a graph referring to the graphs earlier from the section to give you an idea. And a hint here is to think about the y-intercepts. Work on it with your class, discuss it with your classmates, and that's all for this time. We'll see you on the next section of Skew the Script.